Welcome to Electronic Devices and Circuits Lab. In this video, today we are going to learn another experiment. The objective of this experiment is to obtain the frequency response of a single stage common emitter amplifier. So here you can see this diagram, this particular circuit diagram. This circuit diagram is corresponding to the RC coupled amplifiers. So here you can see it is a multi-stage amplifier in which we are having two different stages. Okay, so here we can see this is our first stage of your transistor, which is connected in the common emitter configuration. And this is another stage which is cascaded. Okay, so here in this particular video, we have to learn how this frequency response of this single stage common emitter amplifier can be obtained. So first we will be obtaining the frequency response of the single stage of this amplifier. And later on in the another lecture, in another video, I will be explaining you, I will be adding another this stage, and then we will be see what will be the total frequency response of a multi-stage RC coupled amplifier. So let's begin this discussion. So first of all, here you can see that this is our first stage of common emitter amplifier. So here we can see we are having a transistor, okay, and within this circuit diagram, we can see we have taken the potential divider circuit to bias this particular transistor in a particular mode, okay. So first, we have to implement our transistor, implement our circuit, okay, in the common emitter configuration. We have to choose a certain values of resistance R1, R2, RC, and RE, and we have to choose a certain value of capacitances, okay. A small input signal will be connected to this particular site, this from preceding stage where it is written. So from this two input port, we have to connect the input signal, and then we have to take the output from this particular terminal, okay. Either we can take this output through the capacitor, or we can also connect one more load resistance over here, and we can take the output. So let's see what kind of circuit we have to implement. So here you can see I have already implemented the circuit. Whatever you have seen in this particular diagram, the same circuit I have implemented. The difference is that I have taken the NPN transistor instead of PNP transistor. So here we can see this circuit diagram. Here I have taken this NPN transistor BC547BP, and here are the different resistors. Here we can see this R1 is 33 kilo ohms I have taken, R2 10 kilo ohms, R3 4.7 kilo ohms, and this R4 is 2.2 kilo ohms. I have taken this capacitances to be 10 microfarad. Another capacitance I have taken as 10 microfarad, and here I have taken 22 microfarads. I have connected one more load resistances. So this load resistance you may or you may not be connecting. If you don't want, you can remove this resistance. You can directly measure the output at this point. Okay. So here we can see, first of all, we have to choose this component in such a way that the operating point of this particular transistor, DC operating point of this particular transistor, should be in the active region. So here we can see this common emitter output characteristics. It is a curve between collector to emitter voltage and IC current for different values of the base current. So first of all, we have to choose this values such that this all resistance values, this component values should be selected such that this Q point should be fall at the middle of your active region, okay. So if it is in the near to cutoff region or your saturation region, then you cannot properly design your amplifier. That we have to remember, because in the saturation and the cutoff mode, it can be act as a switches. But to make it an amplifier, we need to have this Q point that should be in the middle of our active region. So that way I have actually taken these values so that this DC operating point of this transistor should be in the middle section. So first of all, what we can do is here you can see I have connected this power supply of 24 volt. And now first we can check it, what is the condition of this Q point. Okay, so what are the different values that we have to see in the Q points are what is the collector current, what is the collector to emitter voltage drop, and what will be the base current. Okay, so if we execute it here, you can see this value. Here you can see I have not connected any input right now. Okay, here you can see I have not connected any input. So only the DC voltage is actually applied to this particular circuit. Okay, so here you can see that this base current is coming out as 7.115 microamperes, and this is our collector current. Okay, this collector current is 2.206 milliamperes, and here we have this collector to emitter voltage drop. Okay, so this is coming out as 8.763. So these voltages and this value of IC is corresponding to the active region. Okay, it will be fall within the active region, and this will be a good condition for making an amplifier, right? So you have to ensure that what should be these values. Okay, otherwise whenever you will make an amplifier, then you may not get the proper output, right? So this is what you have to first ensure. So these values I have already noted down. Okay, here you can see in this actual sheet I have already noted down this frequency response of a common emitter BJT amplifier. I have taken BC547, and these are the DC operating points. Okay, IB in 7.115 microamperes, IC 2.206, and BC is it is 8.763. Okay, so it is wrongly written. It should be 8.7. So this way we are having these values, right? So now you can start your experiment. So how we have to start our experiment, you can see we have to stop it, and now we can make this connection. Now, because we don't require further to measure these voltages, okay, these voltages or current. So we can you can close this all voltmeter and ammeter readings, okay. And here I have connected one source. Okay, it is our function generator. Here you can see this function generator. So I have to first apply a input signal, a very small input signal we have to apply. And then we have to obtain the frequency response of this particular amplifier, we have to vary the frequency of the input signal. Okay, so we will be choosing sinusoidal wave as the input signal, and we have to start varying the frequency from right from 50 hertz. So have to set it at one important point is that we cannot take this magnitude or amplitude of the sinusoidal signal that we are applying as the input to be very large. Okay, it should be a very small value. You remember that the beta value of this BC547 transistor is quite large, and its value is normally more than 300. So because of that, if you take this input signal very large, because of very large gain, there may be a chances that some of the upper portion or the bottom portion of the waveform may get clipped. Okay, and therefore we cannot take very large value as the input signal. It should be a very small signal. Okay, so here I have taken 10 millivolt peak. Okay, so peak to peak signal that will become as 20 millivolt. Okay, that will be the peak to peak value 20 millivolt, because this is the V maximum. Okay, so it is a 10 millivolt V maximum, right? So V peak to peak will become 20 millivolt. So we will start our experiment, and we'll keep this amplitude constant throughout the experiment, but we have to change this frequency, okay, step by step. So I'll be starting with 50 hertz signal. Okay, one important point that you have to remember, that if suppose in your case, in your laboratory, if your function generator is not able to generate such a small voltage, in that cases what you can do is you can make this kind of circuit. Okay, so you just take a potential divider. Okay, I have taken one variable resistance over here. Okay, here you can see that, and because this is a 10 microfarad capacitor, that 10 microfarad capacitor I have connected, and then already we have connected this 10 kilo ohm resistor. So altogether it is going to make a potential divider circuit. And even if you take this like voltage to be 0.5 V peak, means 1 volt peak to peak, if you take, still by adjusting this variable resistor, okay, this potential can be controlled. Okay, this potential you can control. So here we can see that this potential is coming out as V peak to peak value is coming out as 19.6 millivolt. Okay. You remember if in the laboratory, if it is this type of small values, if you are not able to give from the function generator, you please connect one potentiometer, okay, or any resistance, okay, a combination of resistance, so that this potential that we are applying at this point, it should be in the range of 20 millivolt peak to peak. Okay, that you remember if you are making this circuit, right? So now let's begin how to conduct this experiment. So now once we have set these values, okay, so we have to first make this connections, right? So I am just connecting this to this particular point. Now input is applied to this circuit, and this capacitor I have to connect to the circuit. So I have connected here, okay. It is the emitter resistance bypass capacitor that we have connected, and another capacitor is connected at this point, okay. So please remember, you can either connect this load resistance or even you can remove this resistance, okay. There is no very much problem. Even if you remove this resistance, or if you connect this resistance, you will be able to conduct the experiment and you will be able to get the frequency response of your circuit, okay. So here I have taken this voltage probe. That readings of B peak to peak you can directly measure from it. But normally, when we conduct the experiment in the laboratory, it is mandatory to connect this CRO. Okay, because we have to ensure that when we are giving a sinusoidal wave, then the output signal should be a sinusoidal wave, and there should be no clipping of the signal should be observed at the output. Okay, that we have to ensure, and therefore you have to connect this oscilloscope while performing or doing this experiment. Okay, so if you execute now, because all the connections are already made, you can just open this as CRO. Okay, and now we have to properly adjust this time scale, right? We have to properly adjust this time scale so that this waveform will be visible, right? So here we can see, if we properly adjust this, now this waveform is visible over here, right? So now it can observe that if you properly adjust the voltage sensitivity, okay? So at this channel A, and the output is connected, right? The channel A output is connected, and at the channel B, input is connected. So here you can see this yellow line is the corresponding to input. So here you can see this input signal is a sinusoidal wave, and it is of 20 millivolt peak to peak, because here this sensitivity, voltage sensitivity is 20 millivolt per division. So it is covering two divisions. So therefore this yellow wave, which is the input signal, is of 20 millivolt. Similarly, here you can observe that this red one is our output, and this peak to peak you have to actually measure based on this particular voltage sensitivity. Okay, so every time you have to set the voltage sensitivity, and then you have to count how many voltage divisions is being covered by this particular red waveform, and then accordingly you have to do your measurement. On to multisim, we are having some flexibility because of we are having this voltage probe. Okay, so here we can directly see this values, right? These values we can directly see. Okay, so this value which is coming out here is V peak to peak. You can see this value is 636 millivolt. So this value I have already noted down here in this Excel sheet. Okay, for 50 hertz frequency, V peak to peak signal is 20 millivolt. That will be kept constant throughout the experiment. And V output peak to peak we are getting is 0.636 volts, right? Now we have to change this frequency. Okay, we have to make it 100, 200, and so on. So let me do this. Okay, if you make it 100 hertz, okay, let me make it. And if you execute this circuit, okay, here we can observe again, okay, this voltage gain has increased a little bit. Okay, so accordingly you can adjust this all time sensitivity and the voltage sensitivity of your CRO, and here you can see this V peak to peak, which is coming out as 1.25, and I have already tabulated this result. Okay, it is around 1.26 or 1.25. Okay, so this value I have already noted down. So here you can see another value I can show is 500. Okay, let us say if we make it 500 hertz, you can just stop it, and if we make it 500 hertz, we will be getting certain output. So you can see here, when it is 500 hertz, this value V peak to peak is becoming 4.62. Okay. Accordingly, you have to adjust this time sensitivity and voltage sensitivity. Okay. So that you will be able to see the waveform properly. And here we can observe that this waveform is actually coming sinusoidal. Okay. There is no distortion in the output waveform because we are applying sinusoidal wave, the output remains sinusoidal. Okay. For your observation, here you can see this value 500 hertz we have taken. This is 10 volt, 10 millivolt peak to peak. And here we can see this value is 4.62. So these values I have already noted down. Here you can see this value corresponding to 500 frequency. This value is 4.61 and 0.02 is the input V peak to peak signal, right? I would like to draw your attention. Suppose if we change this value, if we make it very large, okay, let us suppose, let me make it something 50 millivolt, okay. So that time this peak to peak value will become 100 millivolt, fine. So if we execute this circuit, okay, here we can see what will happen to this waveform. Here you can see this output waveform, right? This output waveform is actually getting distorted over here, right? It is getting distorted. This bottom portion is getting clipped, okay? Here you can adjust this value. We are applying the sinusoidal wave, but still you can observe that this output waveform is getting clipped. And therefore, I said that we have to properly select the Q point of the circuit, and we have to properly apply the input voltage levels. Otherwise, there will be a certain clipping can be observed in the output signal, right? So let me bring back it to the 10 millivolt, and then again we can carry on our experiment, okay? Because for 10 millivolt, it is sufficient to perform this experiment. Now we can observe this other values, okay? So here I have already conducted this experiment, okay? And I'll be showing you a few of the readings, okay? So here I will be making this equals to, this is, I hope it is corresponding to 20 megahertz or 200 kilohertz. We have to see it is 1 kilohertz. This is 10 kilohertz. This is 100, okay, kilohertz. And this is 1 megahertz. This is 2 megahertz, right? So let me make it 2 megahertz, okay? If I make it 2 megahertz, you can observe this output, okay? If we make it 2 megahertz, okay, and if we execute this circuit, right, here we can see certain waveform, okay? So we have to properly select our this, right? So after this, here you can observe this waveform, right? So still we are getting the sinusoidal wave, and here you can see this V peak to peak is coming out as 6.72. So if you conduct this experiment carefully, you will find that around this 2 megahertz, we are going to get the maximum V output, okay, which is around 6.72. And when you further increase the frequency, this V output value is going to be decreasing, 6.65, 6.63, and so on. Okay, so normally what we do is we have to conduct the experiment and we have to choose those particular frequencies, okay, so that we will be able to completely draw the frequency response, okay. So you just try to take the readings for these values, okay, 3 megahertz, 4, 5, 6, 7, 8, 9, 10 megahertz, okay. This way you go, and then you can get this all readings, okay. One thing that you have to remember is that while conducting the experiment, we are normally interested in the 3 dB bandwidth of any devices, right? So here you can see this is the maximum value 6.72. This is the mid-band gain, right? So this mid-band gain that we are getting is 6.72. So normally the frequency corresponding to 7.707 times the mid-band gain will become the 3 dB cutoff frequency. So this is the lower side and this is the upper side, okay? So because this is the maximum gain, right? That is coming at the middle, somewhere at the 2 megahertz. And even if we reduce the frequency, this gain is actually decreasing. Okay. So it is decreasing. And this 4.75 is the 0.707 times of this 6.72. Okay. And again, at this point 4.75, we are getting at this particular frequency 22.5 megahertz. And here we are getting this value at 530 hertz. Fine. So if you just let me verify this data, 22.5 megahertz. So if you make it 22.5 megahertz, here we can make it 22.5 megahertz. You can observe this waveform. Okay. So again, we are going to get this signal, right? This is sinusoidal wave, and here we can see it is around 4.76 volt, right? So this is what I have written over here. Okay, you can see this value 4.7 V output. So this way you please complete your table, right? First we have to complete this table for all these values. And then we have to find out the absolute gain. Okay, and how to find out this gain? This gain will be the V output divided by the V input. Okay, because V input is kept constant, you can just calculate the ratio of the two. So here are the gains that we have obtained. Okay, this is the gains, right? So this way you can find out at around 2 megahertz, we are going to get the maximum gain, and which is corresponding to 336. Okay, which is whose value is 336. And then again, this gain has reduced by a factor of 0.707. Okay, so these are the two 3 dB points, right? So after doing this experiment, I have taken few data with RL also. So I just told that here I have disconnected the RL. Okay. So if you wish, you can connect this RL also. Okay, at this point, and then you can do the similar observation. You won't find much differences. Okay. Initially, a little bit similar values you are going to get, a little bit deviation you will find. A maximum gain you will be getting is around 6.4. Okay. Otherwise, you will be getting a similar data. Okay. So that you can also conduct if you wish. Now, after getting this gain, I have calculated gain in dB. Okay. So there is a formula. So we have to substitute 20 into log 10, and then we have to take this absolute value, and this way we can calculate gain in dB. So this way I have calculated the gain in dB. And now we have to go for the plotting of the frequency response. Okay. So to plot this frequency response, I have told you several times, but again, you can select this particular data of frequency. And then again, you have to select the other column. Okay. Yeah, I'm selecting this gain in dB by holding the control button onto the keyboard. And then after selecting these two data, you can go to this insert menu, and this is our chart. Okay, so here you can see any chart. So you can take this chart, and after this chart, just you click onto this particular scale. Okay, and here you can take this logarithmic scale. Okay, so this way you will be getting this chart. Okay, this particular. I have already done that so that you can see here. Okay, here we have this curve. So this type of frequency response you are going to get, you are expecting to get. Okay. So here we can see that this is a very small variations, right? Initially, the gain is increasing slowly, and then it will be approaching towards a mid-band gain. So almost at after 1 kilohertz, you can see that the gain is almost getting saturated. There is no much variations, right? Here you can see it is 1 kilohertz, and at 1 kilohertz it is 5.91, and after that it will be almost saturating, and it is reaching maximum up to 6.72. So this is our mid-band voltage gain, right? And then again, at a very high frequency, you can observe that this gain is actually decreasing, right? So normally we are interested in the what will be the 3 dB bandwidth of the transistor frequency response. So here you can see this 3 dB bandwidth that you can calculate by this highest frequency minus lowest frequency. Okay, highest dB point to minus lower 3 dB point. Okay, so if you subtract from this, you will be getting this value 21.970 kilohertz. Similarly, gain, the maximum gain or mid-band gain, if you say it is 36. Okay, so this is the mid-band gain. So on an average, you can take either 336, 335, or 330. Okay, you can take an average value, or you can take the maximum value. So this is our gain. Okay, maximum gain or mid-band gain, you can say. I have also taken this mid-band gain 322 corresponding to when we are taking the RL into consideration. Okay, so that time you can get this gain because 6.44 is the output. So if you divide this 6.44 with 0.02, you will be getting this gain 322. So here one important parameter we generally interested in is the gain bandwidth product. Okay, so gain bandwidth product means it is 3 dB gain, 3 dB bandwidth multiplied with the gain. Okay, so if you multiply, this value is normally coming out as 7381.92 megahertz. So normally the gain bandwidth product of multi-stage amplifiers is always constant. Okay, even if you connect one more stage, okay, that we will do this analysis in the next video. So I hope this discussion must be clear. I will be explaining more about this 3 dB gain bandwidth. Okay, what is this 3 dB gain or gain bandwidth product? I will be discussing in the next video. So if you have any query, let me know with your comment. So thank you for watching this video. Try to implement this circuit and try to make it. Okay, you always first establish a cue point that should be in the center of your cue point, that you have to remember. Okay, and always take care that whenever you are applying any frequency, any voltages, there should be no any distortion in the output should be a sinusoidal wave. Otherwise, you have to choose these values properly. You have to design your circuit properly so that you will be able to get your output. So thank you for watching this video. If you have any query, let me know with your comments. Thank you.